Welcome to the third in our series of getting various aspects of Hadoop up and running. This is the third in a series where we in the first one, we installed Linux on a VMware cluster of 3 nodes. And the second one that involved installing Hadoop using Cloudera Manager. I have installed CDH4 MapReduce v1, and that's what we're using today. So we'll start off by going into the cluster. What we're going to do today is actually run our first Hadoop job, and then our second job using Hadoop streaming and sync sorts DMExpress to create the mappers and reducers. I can't say write because it's a GUI, so it's a lot easier to get started with than a programming language. So I start out when I log in seeing kind of the health of the services that are running. The only thing that's different from the default install was I ended up not uninstalling but stopping and disabling the Uzi service because I'm not using that currently. Now when we look at the hosts, we get a good idea, and this is really a nice thing to look at when Hadoop jobs are running, at what resource load our various nodes have, and there are quite a few more services running on that first node, the -1.vm, than on the others, so it tends to use more memory. And in fact, just sitting at idle and doing very little, it was getting close to actually swapping out with the original memory I had. So I upped it to almost 3 gigs from 2, and I might do some further adjustments once we start running some real jobs here. But just thought you'd be interested in seeing that. Now what we're going to have to start off with is let's get a shell over on this on one of the nodes here for 1-sh, and I'm going to show you a little bit that I had to do with Hdfs. So when Hdfs got first installed, and you'll see on your own cluster if you've followed these tutorials so far, is it had a very minimal type of thing. So it did create a wide open temp directory that various services use for different things, just like a temp directory on your local file system. And there was one user created, a user directory, that is beeswax for a hue. So that was created, but my own, I want my own directory. I'm a user DMX demo on this machine, so I wanted my own user DMX demo directory. So to do that, I had to create it, and I had to give it the permission. You'll notice that directory actually has the DMX demo user as its owner, as does the top level, this DMX directory, where I'm going to put a lot of my projects or my project data in there. So those commands, let's just go ahead and you have to create as the Hdfs user. So the root file system is owned by user Hdfs. So you have to invoke some commands. Here I'm doing Hadoop Fs make dir, so it's make directory, /DMX, and that's how I created my top level directory, and then did a change owner on that directory to the DMX demo user, and did the same thing for the /user DMX demo, and so forth. So I've since created several directories and loaded them with data. But that's something that it's likely going to affect you as soon as you install Hadoop using Cloudera Manager, or for that matter other means. So one of the things that you'll find is you'll play around with the Hadoop Fs commands and say, oh well, let me see, maybe I'll just create a blank file with the touch command, and I'll just call it Gort. And if you do that, then it'll give you a file permission error because basically the user DMX demo or the user Cloudera or whatever user you're in as does not have a directory of its own over there on HDFS. So you notice that I put no path name in there, so it's a relative path of some sort. Well, on HDFS, what that means is that it's relative to that user directory. So if I just do an ls, I see my Gort file that I created, but the true path of it on HDFS is /user/dmxdemo/Gort. Okay, hope that's clear as mud, and you know, hopefully that'll give you some clues to get unstuck from the beginning. So the first thing that you typically do on a Hadoop system is make sure everything's alive and running by running one of the examples, typically the word count type of thing. So what you'll see that I've done is in, where did I put that? DMX word count /input. I've put a couple files in there, an excerpt from Henry V, where he finds out that the Dauphin has given him tennis balls in lieu of the areas that he wanted, and Sonnet 130, which is, you know, one of his great, amazing little quirky sonnets. So I'm going to run word count on those by doing a command from the just from the command line. We'll just run it, and we won't bother with monitoring this yet because this will run quickly enough that there won't be much time to monitor. But the next example will have plenty of data to crunch on, and we'll be able to watch it as it goes along from the different monitoring tools. So what I do is you start everything with a Hadoop command. It has to run a jar file. In this case, it's a little more complicated as to which jar file you get. Sorry, let me do examples.jar. And if you just run that with no arguments, it nicely shows you what types of examples are there. So we're going to go for the word count one. And again, with no extra arguments there, it'll tell us all that it needs is an input and an output. So the input can either be a file or directory. We'll give it DMX word count input and tell it to put the output in DMX word count output. And that way, since I specified a directory, it's going to process all the files within that directory. So we'll see, cross our fingers here, and we did not have a happy result. And the reason, even though you've got a huge stack trace here, is simply that I have to remove the output directory. That's all the way up here. The output directory already exists. So let's have a cow and put a huge stack trace out. All right, that looks a little bit happier. I'll show you what's in that text file. So there's the excerpt from Henry V and our Sonnet 130. My mistress eyes are nothing like the sun. And that is what our word count example is. And has crunched through. So let's take a look at that. If we look at the output file, we can say, first of all, just look at the what it actually wrote out. The directory tends to be a working directory with logs and other information, and your final output, which is, in our case, is part R, blah, blah, blah. So let's just cat that file and see what it has. And there's a bunch of words followed by the aggregated number of their occurrences. And we could go ahead and sort that, say, let's see, it's separated by a tab, and we want the second field, what's it called, field or key? So that'll show us the just sorted the output by number of occurrences ascending. So surprisingly, the is the most popular word in our small sample. So that just gives you the full confidence that Hadoop is in fact running, Hdfs is ready to go, mappers and reducers will work, and so forth. So the next step is to do something more interesting. And in our case, we'll take an example, we'll take the first exercise in Tom White's Hadoop, the Definitive Guide. So in that example, the first Hadoop job was given as weather data. So there's, from the NCDC, there's weather gathered from 1900 to current time from various weather stations, and each weather station produces several readings per day or several readings per hour, whatever the frequency is, and each reading is time-stamped. The weather station that it came from is indicated, and the measurements that it took of air temperature, snow depth, humidity, all sorts of things are recorded and put in a very simple fixed width format, or I should say positional format, because it's actually, the records are terminated with line feeds, but the data is positional in the file. So for us sticklers, that's not exactly fixed width. But at any rate, the data looks like I'm showing here, and doesn't make a whole lot of sense when you look at it that way. So let's take a look at the first, the example of in the file, in the book rather, of the mapper. And you'll see that the mapper expects that it's going to have, it's using a key as a long and a text value, considering the value as text, I should say. And the line that it's taking in is in the value, and the substring, so character positions 15 through 19 is the year, and certain other positional fields are parsed out. So I have the same thing in a DMExpress task called map.dxt. And before I get into what that does, let me show just the data itself. Let's sample the data and see how that's filled out. So the data that I was showing in the editor is actually comprised of these fields. So there's a number of fields that I don't necessarily care about, so they might have names like dummy and field 1 and so forth, and certain fields that I do or might care about, so the station identification, the date of observation, the time of the observation, latitude, longitude, etc. And then the big thing is that we're interested in is air temperature. So that is what we're going to do in our Hadoop job, is find the maximum temperature per year from all of the stations that recorded data. In any of these fields, if you see something filled with 9s, if there's a particular measurement field and it's filled with 9s, that means that measurement is invalid. So either the weather station doesn't record that particular parameter, or it was faulty for some reason or suspect for some reason, and it ends up in the file as all 9s. So we want to filter those out and ignore the ones that are all 9s. And then there's a couple other things that we'll see if we look at this Java code. So the Java code is saying, well, if, first of all, it's defining all 9s as a concept that means missing. And so it says if the air temperature does not equal missing and the quality is one of these digits, so it's either 0, 1, 4, 5, 9, and I forget exactly what that quality reading means. But if it's not those things, then it's okay. If it's one of these qualities, then it's a good reading, and if it's not all nines, it's a good reading, and therefore will output basically the key will be the year, and the value will be air temperature. So the very simplest case, a simple value is the key, and a simple value is the value. If we look at my DMX task, we'll see that I do exactly the same thing as the Java code does. Let me pull that up. That the mapper tasks, so this is what we're doing. We read from standard input because Hadoop is going to feed the information. It's going to feed a split of data to our task. So therefore the task receives its input from standard input. It does not read a file. The file is handled in chunks and given to us by Hadoop. And then we've got a filter that says retain records that satisfy this condition. The temperature, the air temperature does not equals 9999, and the quality code is one of these values. So we use a function in DMExpress called if equals any. And we built that with a nice little handy expression editor that DMExpress comes with. So all this stuff is very, very simple to define. And then what we're outputting, remember a mapper's job is to parse the input and then make the output conform to, if you're using a native API, you actually emit a key and a value. If you're using Hadoop streaming, you output a key followed by a tab or whatever delimiter you're using, generally a tab character, and the value. So it's the Hadoop streaming is of course serialized, so everything's in kind of a simple text format. So that's what in fact this mapper task is doing, that it's reformatting to say, well, we're going to take date of observation and substring it to output only the year, and then we're going to, the next field will be the air temperature, and the field separator is a tab. So that's all handled for us, and just like the Java code did, I actually named the 4 nines as a value. Now, of course, I didn't actually put that in my filter because I forgot, but what you could do is instead of writing the formula that way, you would say the condition is missing and etc., etc., or it should be, not equal to missing. Anyway, I'm going to leave the filter as is because I know it works as is, so that's good enough. And then our reducer, remember the reducer is going to see the Java code here. The reducer is going to see a certain set of keys, so of years, and those keys will have a collection of temperatures with them, and the job of the reducer is to return the year and the maximum temperature. So the way that looks in the DMExpress GUI is kind of similar. We've got our input coming in from before, which is year and air temperature, and then we define an aggregation. And our group by field is the year, and our output is the maximum of the air temperature. So we're going to see a number of records rather than a collection of values, because that's the way Hadoop streaming does it. But this aggregation task then will output just the maximum. And I've indicated as a performance enhancing type of thing, or an efficiency, function that I've indicated that each source is pre-sorted on the group by fields, because Hadoop will have already sorted on the year before the reducer sees it. Therefore, the disaggregation task doesn't have to resort it. And because this is DMExpress and it's a super efficient engine, and I don't want to have to start it up over and over again, I'm going to try to feed it really, really large splits of data. So much, much larger than the block size. That's what I'm going to prefer, so that the DMExpress engine has more to work on and can be more impressive and awesome in its efficiency by dealing with large chunks at a time. So it's less efficient to have many, many small chunks processed when you're using DMExpress. All right, and my output is going to be very simple. It doesn't have to. It can be anything. It no longer has to conform to, key value pairs or anything like that. The output of the final reducer that is going to persist to Hdfs can be anything. But in this case, I don't have much else to output, although I could add a count or something like that. But I could add a count. But all I'm doing is outputting year and the air temperature. And what I'm doing here is dividing the air temperature by 10, because those temperatures that you saw before are actually in there's an implied decimal place in those. As a matter of fact, if we quickly look at this again, the data for air temperature minus 0094, that actually means 9.4, minus 9.4 Celsius. And you might have positive or negative numbers, and so there's that one implied decimal point. So my final data will actually persist that. All right, so let's just get to it. And what we're going to do to invoke Hadoop streaming is we're going to use to reference the streaming library. This is the right one in my case for MapReduce 1 on CDH4. And I'm going to add some additional parameters here. So I'm just as a nicety, adding a job name. As I said, I want to feed DMExpress tasks a large amount of data, so I'm going to try to up the minimum split size by a lot. If my block size might be only 128 megabytes, but here I'm saying I will prefer that each map task see at least 1 gigabyte of data. And it's not going to be the case, because a lot of those early years there wasn't much data collected. So it's only in the later years that there's, that a single year's data is going to be in the gigabytes versus megabytes or even hundreds of kilobytes, like you have in the early 1900s. We're collecting more and more data. I'm additionally going to say, tell Hadoop streaming that I want that I'm using a numeric key, basically. So this -n option tells Hadoop to sort it numerically. Of course, we're dealing with 4-digit years, so it could be sorted textually also, and we'd get the same result. But it's a good thing to know that you can specify how to control the sort. I'm saying we want 3 reduced tasks. I'm telling it where the input is, and notice I'm not using all of the years. I'm just saying 1910 through 1919 with this wildcard, so that we can start with a smaller amount of data, and then go from there. And then the files that I have to copy over here, I put in file commands. So I have the script that runs the mapper and the DMX task itself. Any related files that I need associated with this job to run, I specify on -file parameters. Or actually now there's a single parameter called -files, so where you can put all of them in one parameter separated by commas. And then finally, what is my mapper and what is my reducer? Notice the mapper is not that DMX task that I created, but it's a shell script. So what does that look like? Well, it's very simple. It's just if it needs to set environment variables, then it does. And then it uses the DMExpress task to run, or command to run that task. Now, this is actually redundant because I've made these environment variables global on the systems, on the nodes, but just for safety's sake and in case I run it on a different system or whatever, I put those environment variables in the first part of the script. The reducer script looks exactly the same. Neither of them is doing anything fancy. It's just running that final task. So let's take a quick look at what that input directory looks like. Not word count. Let's go let's go to NCDC. There we go. So as you see what I was saying before, the 1901 data, we're under a megabyte for all of the records collected in those years. And then we start getting up into the megabytes in the 1910s and so forth. I go up, my data that I have is only through 1950, but you see it starts to leap up. And in the 50 years since, oh my God, it's really exploded, and it really is kind of a large data set. So I haven't. Next time I'm in a very high bandwidth place, I'll grab some more years. But let's take a look at just running this job, and then we'll actually this time monitor the thing. So I'm going to do my run streaming command that we had seen before. And everything that you used at CDH3 is now deprecated because they've changed paths, they've changed environment variables, they've changed command parameters. So you get a lot of those deprecated messages. So let's go back to our friendly web browser and take a look at what's happening on our hosts, and we'll monitor their resource usage as they go. And then I'll show you a cool thing here. Looking at the Hue service, let's take a bigger look at that, and oh, there's a link to the Hue web user interface. So that's cool. And I can go and look through files and look through jobs. So it so happens that there's a highest temperature job running. And that's one way to view your jobs. Now another way, which is probably more familiar, is on port 50030. Oh, what happened? Is that already finished? Oh, it already finished. Sorry, I didn't quite get to that in time. Don't worry, the next run of this job will be with much more data, and we'll have lots of time to look at it. So this job already ran, and let's just go back to Hue because it's got a very nice file browser as well. And our output was in DMX NCDC output. And I specified that I wanted 3 reducers, so sure enough I have 3 output files. If we look at them, remember I told Hadoop Streaming that the key was numeric, and I want 3 reducers. But I did not say how I want the data partitioned between the reducers. Therefore, Hadoop says, well, numeric key, I'll just do a modulus. So it just did modulo 3 on the year, which is the key. So each file will have, you know, the mod 1, mod 0, mod 2, whatever it is. So I'm looking at 1910, 1913, 1916, and seeing the high temperature for those years. If I look at another file, I'll see other years. Isn't that cool? So that's the partitioning, and you don't have to specify it. So let's clean some of this stuff up. We'll run a job with all the data and look at some more monitoring things, and then we'll be done with this one. All right, so what I'm going to do is actually change my streaming script. Change my streaming script. I'll say that 20 times before I have to put marbles in my mouth. All right, and we'll use all of the input. Go back to the shell and run that again. All right, so there's a couple things that I'll point out. One was that first job I ran, based on the amount of data there was, or in this case really the number of files that there were, it created 10 map tasks. Now with much more data, when I look at that job, it created 59 map tasks. And if I didn't have that split size up to 1 gigabyte, then there would be more map tasks, but there would not be many more map tasks because the great majority of the files are under 1 gigabyte, but the way the split goes, it will be either your split size or the file by itself. It won't be a concatenation of multiple files. You can do that with some trickery in the native API, but not in Hadoop streaming, I believe. But you can watch this job progress, and some of the, as you know, you can see some of these, because of the way the split goes by file, some of these tasks will have a lot of data to work with, and some will have very, very little. But we'll see some interesting things that we're seeing. Let me refresh this. Okay, so 4 mapper tasks have completed. There are 6 running. There are generally 6 running at any given time. Why is that? Well, let's see. This task ran on 4-3. This one on node 4-2. This one on -2. This one on, -1. So basically what it's doing is apportioning 2 tasks per node, and that's on account. Basically, it's on account of I have 2 cores on each machine and a limited amount of memory. So those are called task slots. I can manipulate the task slots in various ways by changing memory, by changing allocations, and doing it directly and indirectly. But you'll see that if I overwhelm this and say, yeah, I'll run 100 tasks on this machine, that it will probably overwhelm the resources. In fact, if we take a look at at how the hosts are performing, okay, we're in pretty good shape. We're not swapping currently, although there has been some swapping. And you can look at this to get a broad idea of how your nodes are doing, and if you need to adjust configuration parameters, or if they're VMs, give them more memory. Actually, if they're standalone machines, you could give them more memory as well. And so you've got your diagrams of what's completed down here. And in between, some very interesting numbers. Since I'm kind of interested in whether I'm swapping or not, the first thing that I think to look at is spilled records. So this is when the intermediate outputs can't be kept in buffers, in memory buffers, and have to be written out to disk. So in DMExpress, it's like using workspace, and you try to avoid having workspace by telling the sort task, telling the join task that one of the sides is pre-sorted, and things like that. So you do the same type of thing in Hadoop, but there are many, many, many more moving parts and many more configuration parameters to deal with. So this is telling me that all the mappers have completed. The copy stage is basically the shuffle stage. The reducers have received their input, and their input is all lined up and ready to go. The sort step that happens at the reducer stage has occurred, and now they're actually doing their processing. And now they're all done, and the job is all done. Ran in 4 minutes and 24 seconds. And now when we look, we still have 3 files, but there's more years. So that is all we have for this section. I'm going to do another couple of videos on some more advanced topics, like doing joins that are where both sides are too large to fit in the on the local file system, and some other things, and mostly using DMExpress to illustrate those. Going to limit my audience, I'm sure, but I hope you see the advantage of using a GUI for this, and of using Hadoop streaming. When we want to go to the native API, then we've got a template, a working template, to know exactly how things work. Actually, I'm going to give one bonus feature, if for those of you who haven't fallen asleep yet, which is when you're using Hadoop streaming, you can do stuff from the command line, which is pretty cool. So if I do, for instance, my cat command, but I do it on an NCDC data, yeah, okay. So you can actually test your streaming job as you go. So let's say I'm looking at 1911.dat and looking at the first few lines of that. And then I want to see if that data is actually going to work with my mapper. Well, I can pipe it to my mapper. It's very simple. Before I run Hadoop, I can do that. So I see my output here, which is good, but I also see a bunch of the logging information, which I may be not interested in. So I'll redirect standard error. And sure enough, there's my data. And this is Hadoop saying unable to write to output stream. That's just because I interrupted it with the head, so the pipe got interrupted. So don't worry about that last thing. Then I want to do my reducer, but the reducer is going to see everything in a sorted order. So what does that mean? Well, I have to duplicate that functionality by sorting here. So on the command line, I can say something like got tab and key 1. Okay, this isn't going to be very interesting, so it's all 1911, but you get the idea. And then finally, you can pipe that to your reducer just to make sure that works. And once again, I'll do the log errors to dev null, and there's my answer. Now, there's another thing I can do, and I know I don't have this installed. Yeah, there's a nice little package called randomize lines. And to solve the problem of being too boring with only 1911, let's do 19.1 star.dat. So we'll get 1910 through 1919. And randomize the lines, and then do, I don't know, maybe just 10,000 records from that, and run the whole thing and see what we get. So this is a little miniature Hadoop job right there, so that you can test your logic and test that your data is going to work correctly. And in fact, I could probably do this very same thing without sampling the data at all, because it's a pretty small sample set and DMExpress is incredibly fast. So there you go. Those are the numbers we should actually see in our output when we run Hadoop. So hopefully this will be helpful, and that's all we have for this session. Thanks.